An equation in the form of ax is equal to b can be rearranged into x is equal to a inverse times b. Just multiply both sides by a inverse. There's a formula for a inverse, so x is equal to 1 over the determinant of a times the adjoint of a times b. And here in this example, I'm going to have A be a 3 by 3 matrix, x11, x12, x13, etc. And also I have this written out in x, y, and z form. So x1, y1, z1, x2, y2, z2, x3, y3, z3. 3 different equations with 3 variables. And for the constants, b is equal to b1, b2, and b3. So the first thing I'm going to do is just replace what I can in this formula. So I have x is equal to 1 over the determinant of a times the adjoint of a times b. I can find the adjoint of a easily enough. Just make a cofactor of matrices and then turn it like this. That's the adjoint. So the adjoint is equal to c11, c21, c31, x11, x21, x31. The columns are now the rows, and the rows x11, x12, x13, c11, c12, c13 are now the columns. And this is going to be multiplied by b1, b2, and b3. We can multiply these together. The result is going to be a 3 by 1 matrix. So c11 times b1 plus c21, b2 times c31, b3. And this is just one entry. It looks like it's not, but these are all being added together. So 3 by 1. So 3 rows, 1 column. And what I wrote this out here for is just to get it, it's just to easier see what's going on in this final step, to show exactly why this is working. So instead of c11, c21, c31, I'm going to write it in terms of x, y, and z. So if I replace all of these, c11, that's x1, c21, that's x2, c31, that's x3. You're going to notice that in each one of these entries, in the top entry it's nothing but x, and the middle entry it's nothing but y, and the bottom entry is nothing but z. So from here we've got to talk about determinants again. If I want to find the determinant of matrix A, that's easy enough if we want to use a cofactor method. Let's just use the column. So the first thing what I'm going to do is just find all the cofactors. The cofactor of x11, the cofactor of x21, the cofactor of x31. And then what I'm going to do is multiply all those cofactors by their corresponding entries. So the cofactor of x11 by x11, the cofactor of x21 by x21, cofactor of x31 by x31. And that will give me the determinant. If I look at this formula here, if I go down the rows and get the cofactors, so the cofactor, if I take the determinant from here, cofactor of x1, cofactor of x2, cofactor of x3. If I want to get the determinant, I multiply the cofactor of x1 by x1, x2, and then x3. But here, this is multiplying the cofactors by b1, b2, and b3. So essentially, it's as if the entries were b1, b2, and b3 for this first column, because the cofactors are going to be the same. Because the cofactor of now b1 as this entry is still going to be this determinant. Cofactor for this second entry here is still going to be this determinant. So it has nothing to do with what's in this actual row, or column I should say. And this is what Cramer's rule is. Cramer's rule replaces x, y, or z, if you want to think of it this way, a column with whatever b is. So b1, b2, and b3. And that will give me this. And the reason, and it's also important, I guess here's what's important to know, because it's equal to x, but someone might ask, well, what about this row and this row? Don't those equal anything? Well, if you think about it, let's say we did the first row, or I mean the first column. So we're going to get whatever this is. It's going to be as if this determinant were taken with B present. But now if we move on to the second value, y, I'm taking the cofactors of this, this, and this, and then multiplying it by these entries. So right now I've got this, right? But if I do what this says, this is going to multiply everything again instead of by, well, I don't want to use both of these, so instead of multiplying it by y1, y2, and y3, it's again going to multiply it by b1, b2, and b3. So I've got a situation where really I've got two of the same column or row, and when I've got two of the same column or row and I take the determinant like this, it's always going to be 0. So I'll put, I did an example for why that works for rows, but it's the same thing for columns, so I'll just put a link there. But the whole point is that whenever I replace one of these rows with, or one of these columns, I keep saying rows, whenever I replace one of these columns with B, the other entries are going to be 0, because it's going to be like I'm taking the determinant with two of the same column, which will be equal to 0. So when I replace this first column with B, these are going to be 0. When I replace the second column with B, these two are going to be 0. And when this last column gets replaced with B, these other two are going to be equal to 0. And the point is that each one of these rows is just one thing. It's just x, or just y, or just z. So when this is taken, this x value is only going to be the z value, or the y value, or the x value. So it's written as xj is equal to b1 times c1j, b2, c2j, plus b3, c3j over the determinant of A. And the reason that it's only this j value, the j value is just a column C. C1j, so 1, 2, 3, so it's just like this, this, or this. The reason it's not equal to all these three is because whenever we replace one of these columns with B, the other ones are going to be equal to 0, so we just say that xj is equal to this formula. Alright, never mind, but that's why Cramer's rule works.